So what is the question? The question is the following. We have a set of polynomials. And n polynomials in d unknowns. And we want to answer two questions. Are there solutions to f of x equals 0, where f will be just f of x will be just the vector f1 of x, fn of x, and second question: can we find them in polynomial time? Say efficiently. And okay, traditionally, the part of I will overview what is known about this problem, a little bit of what is known, and the traditional setting for this is to assume that the fi are homogeneous polynomials, and therefore x equals 0 is always a solution. So you have to put a constraint, and you normally put the constraint that the norm of x is equal to 1. Or equivalently, if you look in the math literature, this means that you are working on the projective space. Okay, so often things are stated in that form. So what is known about this problem? Okay, obsession. This. Okay, let's work here. What is known about this problem? Well, if x is in C to the D, so if my unknown are complex, then question 1 is answered by Bézout theorem. And Bézout theorem says that generically, if n, so in this case, okay, one typically looks at the edge case in which there are basically as many equations as unknown. There is one equation because of the norm, so there is in reality n plus 1 equation. So here is as many equations as unknown, and Bézout theorem says that there is, generically, well, if you have one polynomial in one unknown, the number of solutions is the degree of the polynomial, and in general, it's the product of the degrees. This is the degree of fi. And now, so this is a very classical theorem. It's the first theorem in perhaps algebraic geometry. The second question is much more difficult and was asked by Steve Smale in 1998. Question for random fi. Of course, if you don't assume anything about fi, this problem can be, is NPR'd, but asked what happens for random fi, and Smale listed as a list of problems for, kind of a repetition of Hilbert list of problems for the next century, and this was one of the problems that was solved by Lairez in the affirmative in 2020. Okay, so this is the setting, the situation for the complex case, but as you know, solution over the complex is easier to find them than over the real. So what happens if my vector is real? Well, for question 1, always looking at random polynomials, and I will describe what I mean by random polynomials. Fi. Okay, all of this is about random FIs. question 1 was addressed by Eliran in last year again. And what he proved is that, the number is not deterministic, but basically concentrates around the square root of the Bezout number. And this is a probabilistic statement. Okay, so without probability, the number of solution is close to the square root of the Bezout number. Okay, but he didn't ask about, algorithms for finding such solutions. And okay, so this work, what we do is, this work. Okay, we have a paper that is on the archive, another one that will be soon out. So we look at one non-homogeneous polynomials and two the computational question. All of these over the real, so algorithmic question.
There are algorithms to find all solutions?
Find one solution. So the question is to find one solution. Okay, so what will be the model? The model will be the following. So this is basically the model proposed by Smail in a slightly different languages. Is that the phi is, so the phi is, okay, I'll do, so our function on the sphere. And these are independent Gaussian processes with covariance centered Gaussian processes with covariance where this is the inner product, the usual inner product, right? And okay, so the xii's are polynomials. Now, in reality, throughout the talk, I'll keep the xii all equal, just for simplicity, but the things can be, okay, I'll mention some generalization. Right, so these are polynomial, this can be constructed explicitly by saying that each of f of x is the sum over k 0, and then there is square root of psi k, where psi k is the kth coefficient of this polynomial, and then sum over I1 ik 1 to d g I I1 ik x I1 x ik. Okay, if these g's are standard normal, IID standard normal, then this polynomial has this covariance and vice versa. Okay, so I will sometimes consider a special case because I don't want to write too complicated formula, but all that we do with this general setting, and the special case is the one in which xi of t is xi 0 plus t to the p. So it's a constant plus an homogeneous polynomial. Okay, and the constant is because I don't want 0 to be a solution. I want to make my life a little bit more difficult. Now, I should mention that this model was studied for a completely independent reason very recently in physics. By Jan Fyodorov and most notably by Pier Francesco Urbani, 2023. So he has non-rigorous results about several of the things that I'll talk about, and he has also a very nice name for this model. It calls it the canyon landscape model. Because as you will see, there is an energy function, and this energy function has kind of canyons. So that is, very flat valleys.
Still have the projective assumption, like the norm assumption.
Yeah. Throughout I'll fix norm of x equal 1. So I want to find a solution. I'm given, so the problem is I have n polynomial that are generated by this process, and then I want to find solutions of this on the sphere. Any question? All right. So one other element of the question is that we'll consider the limit, the high dimensional limit, n over d, n and d going to infinity, and n over d going to constant alpha. That will be in 0, 1 typically, 0, 1. And okay, it could be also bigger than 1 actually, doesn't matter. And okay, the first question is, are there solutions? And the natural conjecture would be that depending on the value of alpha, there will be with high probability solution or not, right? And so I defined 2 thresholds. Unfortunately, we cannot prove this conjecture, so this is the first open question. So I define an upper threshold, so let's say inf of alpha such that so let me define the set of solution as n d epsilon. So this is the set of x such that x is equal to 1 and f of x. F of x typically is of order n because each entry of f is of order 1. So at a random point, this will be of order n. I ask this to be less than n times epsilon, and I ask that okay, did I do it in the correct order? Okay, so this is the smallest alpha such that with high probability, basically there are solutions, almost solutions, so solution up to a tolerance epsilon, and then there is the largest alpha. This is the smaller alpha such that there is no such approximate solution, that there is the largest alpha such that there is exact solutions. Okay, so first open problem. Okay, conjecture. Natural conjecture is that at least for generic psi, alpha bar is equal to okay, so now I will summarize the results that we have on there. So it's the problem. Okay, and of course another, so this is the existence question, and there is a related question, give me an algorithm and define the threshold above which this algorithm can find the solution. No? You can imagine that if you have much less equations that are known, that is very easy, otherwise it becomes hard. Okay, perhaps I'll write. Yeah. Okay, so the first, we have some results about these thresholds for existence of solutions, but I will not spend much time on them. We have an upper bound on alpha per psi, and I will not write it formally, but I will just write it in the case of the example that I wrote there. In the example that I wrote there, this gives me alpha bar of psi 0 in P. this is less or equal than log p over xi 0. And the lower bound always in the example gives me that this is, so for large p, this is basically log p over xi 0, and this is for large p is also log p over xi 0. So here I'm assuming that xi 0, in bracket in this xi 0 is bigger than log p. I mean, this OP can be less or positive or negative, if you like it like this. Okay, so this is the first thing. You can upper and lower bound this threshold, but it's open to determine that there is a tight threshold. Okay, so this is about the threshold. The second question is about, the question that I want to focus on is about the algorithm. And the first algorithm that you might want to think about is gradient descent, right? Or gradient flow. Okay, so this is gradient descent. I have to define a cost function. The way, a very natural way, the way that we use this, that we just take half of the norm of f of x squared. Okay, so you have square loss basically, and we try to fit this equation with square loss, and we run gradient descent on it. All right, so the question is for which alpha does this succeed? Sorry? Yeah, the constraint is x equal 1. So really what we do is projected gradient descent or gradient flow on the sphere, Riemannian gradient flow. So let me write the result for a gradient flow. Just explicitly, we start with a point uniform on the sphere. And then we run x dot equal minus projection of the tangent space of the gradient of x. And the projected one is just that, the obvious one, okay? Okay, so unfortunately, analyzing this thing, as some of you know, it's a pain, right? And analyzing it for random problem is a pain because the randomness get mixed to the randomness of the landscape get mixed with the in a very non-trivial way with the algorithm. And so, okay, this is the theorem that we have. There is a threshold that we call alpha GD of xi. And okay, I can write you a formula. I'll write you a general formula for this. This is a constant times xi prime of 1 square divided by xi second of 1, xi prime of 1, log of xi second of 1 over xi third, xi prime 1. Okay, there is some such threshold. And if this happens, so if then with high probability, well, the energy goes down exponentially. For some constant means n independent quantity lambda positive all t. Okay, so you find there exists a solution beyond this threshold, and gradient descent finds it, right? Now, if you look at the special case, so on my running example, and you specialize this to that special case, you get alpha GD psi 0 and P. This is basically, let's see, is bigger, or it's all right, so it's a factor, a big factor below the threshold for existence of solution. So there is the large interval in which we know that there are solutions, but we cannot prove it, or we cannot find them via gradient descent, gradient flow. Okay, so with a large gap. Yeah.
So I was looking at gradient descent for tensor factorization. And there's like a gap between where you know there exists factorizations because they're NP-hard, like an overparametrization ratio where they improve gradient. Do you think there's like NP-hardness?
If there is hardness here, but the problem is worst case hard, right? Now in average case, there is no hardness result to date, but yeah, I mean, I think that we can prove some restricted hardness result, but we didn't prove it yet. Okay? So I think that there is a substantial gap. Still, I don't think, as you will see, this thing is not optimal. Right? So this threshold is not optimal, it's substantially suboptimal. Now there are two things into this. One is, of course, that gradient descent needs not to be the optimal algorithm for this problem. Second is that, okay, what is the analysis of this algorithm? The analysis of this algorithm is basically the same analysis that people have developed very recently for analyzing gradient descent on neural network via this locally linear approximation, like neural tangent approximation. So local analysis. Indeed, if you look at the proof of this theorem, in this proof we prove not only that this converges to 0, but it converges to a solution that is very close to the initialization. Okay, so what is the picture? The picture is that I have my unit sphere, and then the set of solutions here is a very, so this is the unit sphere in d dimension, and the set of solution is a manifold of dimension d minus n, so it's a very high dimensional manifold, and if I start at a random initialization, I converge very close. So if n minus d is d minus n is large enough, analyzing the gradient flow locally around the random initialization is sufficient, right? And in this case, if you carry it in this simple model, if you carry out this analysis that people have done it in deep learning, it yields this result that is substantially suboptimal. Okay. And there is really little that can be done about it. All right, so this is why we turn to another algorithm that is Hessian descent. So this was analyzed, similar to something that Eliran did in the case of spin classes, and here we adapt it to this problem. And what is the algorithm? The algorithm is very simple. Okay, we initialize our algorithm with a point very close to the origin. And then, okay, for k less than 1 over delta, okay, we repeat the following. We find a vk that is orthogonal to xk, so in the tangent space, such that, okay, find the vk Hessian of h at xk, vk is less or equal than minus than lambda mean. This is the Hessian. This is the Hessian. Perhaps with some error. And then we go along that direction. Okay, we go along that direction, and okay, we do, there is a little thing here you have to do here to avoid being hurt by the gradient. You put a sign, and you take it to be sk is the sign of bk times the gradient of the Hessian at xk. Does the algorithm make sense? So the algorithm is not, unlike the projected gradient, is not moving on the surface of the sphere, it's moving inside the ball. Okay, and so it starts at the origin, and then take a sequence of orthogonal steps. Now I cannot do more than 2 orthogonal steps on the blackboard, but okay, imagine that the third one is orthogonal, and then it ends up on the surface of the ball. And at each step, what you look at, well, you look at the tangent, the orthogonal thing, the orthogonal space to the current position, and you will move in the best direction for the Hessian, and you essentially neglect the gradient except for choosing the sign of the direction not to be hurt by the gradient. Now, the beautiful thing about this algorithm is that we can now come up with a pretty theorem. Okay, apart that it is an interesting algorithm, we can also come up with a pretty theorem. That,
You just take sign of that.
Sorry?
Like sk is just the sign, plus minus.
Yeah. Because you don't want to, if you look at the Taylor expansion, I mean, you want the first order term of the Taylor expansion to have the right sign, but you don't care about it. We just care about gaining energy from the Hessian, okay? And the other thing that we care about is, what is the other thing that we care about? I mean, the other thing that is interesting about this algorithm is that here delta is a constant. So we have a constant number of steps, right? This is square root of delta, right? Because each time, xk plus 1, just by Pythagoras theorem, is xk plus square root of delta square, so plus delta. So in 1 over delta terms, steps, we end up on the boundary on the sphere.
So I have probably a very stupid question.
No. There is no stupid question.
So the Béjot theorem and so on for projective spaces, you are getting the number of solution, which is so you can count the number of solution because it's a projective geometry. Whereas here you have a
manifold.
A manifold. So there is a discrepancy, right? So because so here you can have uncountable number of solution.
Okay, but I agree. It's a manifold. You have uncountable, but there is still a notion of solutions, and we can try to find.
Right. But we are only concerned about existence, so we don't even care about.
Right. So at this level, there are solutions, and there is many of them. There is uncountably many. It's still unclear that I can find them.
Sure. Okay.
But I haven't even. That was a great question. I haven't really.
Yeah, great question.
When the polynomials are linear, what is this algorithm used to?
That is an excellent question. It comes in 5 minutes. It's on my list. I will address. In fact, this algorithm does very poorly if it is linear. Okay. It's good that you started the questions.
First word. So log p is in denominator, but on the second word you have log p in numerator.
Right. So
that's the gap.
So that's the big gap. So here I know that there exists.
You wrote it just.
This is for GD. So GD needs 2 log p. I don't know if it needs GD, but our analysis of GD needs 2 log p factors. Log p factors. Okay, so this is the theorem. Okay, now I'll write some formulas. Some of you might like, some other might not like. Okay, for alpha in 0, 1 and AB positive, let me define the following function QM comma alpha AB. This is minus 1 over M plus alpha B 1 plus Bm minus A square M. And then I'll define Z star of alpha AB to be minus sup over M positive of Q M alpha AB. And then solve the following ODE. U dot of t equal minus 1 over 2 alpha z star of alpha square root of 2 alpha u of t xi second of t xi prime of t. Okay, this is a ODE in one dimension that you can solve with initial condition. Let me write it here because I don't want to use too much space, 1/2 xi of 0. And then the claim is that if I look at the energy, that I remind you is the square norm of the output of Hessian descent, this is, okay, we really prove is less or equal. Okay, so this gives, okay, here in the theorem we formally prove with less or equal, but the analysis is sharp. So, modulo a few more pages, this should be an equal. So this gives a characterization of the energy that is achieved by this algorithm. So the analysis is sharp, unlike in gradient descent, and this allows to define a threshold. Alpha HD of xi is the first alpha at which this becomes 0, right? I mean, becomes non-zero, okay? So if you plot this as a function of alpha, this energy at which you arrive, this is 0 and then becomes non-zero after a certain point, and this is what we call alpha HD. It's the largest alpha at which this algorithm gives me almost solution. Now, if you compare it with this, what I wrote there, okay, perhaps I'll erase a piece of board here. You can bound the solution of this object, and you get that alpha HD for my toy model. For my running example, this is 4 over xi 0 plus molo p of 1 and 4 over xi 0 plus 1 plus molo p of 1. Okay, so 2 remarks. First of all, we didn't close the gap. Second, this is much better than this. Okay. Okay, so perhaps I should spend a word about where does this, all complicated formula, where do they come from? Because, okay, the formula are long. I brought them just to show that you can get something very explicit. But where do they come from? Well, they come from analyzing the Hessian of this energy at a point, right? The energy is the, remember that the energy, I have it somewhere, energy is the norm square of f divided by 2. So if you take the gradient, you get df of x, df x and then there is a transpose here, plus sum over I 1 to n phi of x Hessian of phi of x. Okay, and okay, if you take a fixed point, the joint at fixed x in the ball, if you look at the joint distribution of these three, if okay, ux is a basis for the perpendicular space, what happens is that f of x is square root of psi q times g, where g is a standard normal vector, and then df, okay, let's say ux is square root of psi prime of q times z, where z is a matrix with IID normal 0, 1 entry, and this Hessian is square root of psi second times wi, where wi is a GOE matrix. So it's a matrix with IID Gaussian entries, right? Therefore, you understand that, okay, if you look now at the Hessian, this will be, at a fixed point, will be, okay, this part gives psi prime of q times z transpose. So it's a Wishart matrix times a coefficient, and this is a sum of GOE matrix, right, which is itself a GOE matrix. So you get something like, let's see, square root of psi of q, psi prime of q, psi second of q, and then norm of g times w, where this is a GOE matrix. So the Hessian has a very nice form, as a part that is, positive definite, that is a Wishart matrix. This is positive definite, but it has a part that is, you see, this part of the Hessian is positive definite. But since we are over-parametrized, there are lots of flat directions. And then there is a part that is not positive definite, that has some negative directions because it's a GOE. The only thing to pay attention to is that the coefficient in front of this GOE is correlated with the energy itself, because the energy will be the norm of g squared. Okay? So as you go down and down in energy, this part disappears. Okay? This is why there is this canyon landscape. There is a lot of almost flat directions. At high energy, this flat direction have a negative component. Flattish direction have a negative component. But as you go down in energy, they become flatter and flatter. Okay, so this is the canyon landscape. Now, how the analysis of this goes? Well, the analysis of this goes by simply computing what is the minimum eigenvalue of this matrix. Now you would say, okay, but this is the matrix at a fixed point, it's not the matrix at any point. If you run the algorithm, you might find very strange point. But the point is that if I fix this coefficient here, eigenvalues have very strong concentrations properties. In particular, the probability of an upper deviation, okay, let me perhaps write something about this. Okay, let's write it here. So the key remark or lemma, I'll write it informally, is that conditional on h of x equal U. So what this ODE traces is really this energy per constraint, and conditional on that, this function Z star is simply the meaning of being the minimum eigenvalue of this Hessian at X. So this is -1 over alpha Z star of whatever, right? Alpha square root of 2 alpha U psi second of Q and psi prime of Q. Okay, so if you give me plus small of 1. So if you fix a point, and you know that this point has energy U, the minimum eigenvalue is exactly the form that I brought here on the ODE. So the meaning of the ODE is simply the energy decreases by the amount that is given by the minimum eigenvalue, which is clear. And the important fact is that the probability that this is bigger, so you gain less than you want. Okay? So let me call this lambda 0 plus t plus okay. T I used it already, plus S. This is e to the minus n square C of S. Right? So all the crux of the thing is that here we have concentration at rate n square, so this is uniform over all the board.
So when you conditioned on this, so Z is not,
so
not Gaussian anymore, so it's like some conditional.
No, yeah, but in this case, these are all independent. The distribution is that these G, Z, W, I are all independent. If you restrict, okay, I should have written here UX transpose UX. If you restrict on the tangent space, these three things are all independent. So conditioning on this means simply fixing these two.
I see. So, okay. So this will follow from Gaussian.
Yeah, it's just simple calculus. You compute the covariance of these objects, and they happen to be independent. Okay, now to Rachel's question, is this optimal? And the answer is no, because of linear example. In the linear case, linear case is just psi of t equals psi 0 plus t. In my language, okay, you can either plug in the formula or listen to what I said. In that case, this part is 0, right? And so the Hessian is positive definite at every point, and so you will lambda minimum will always be 0, so this will be 0. You will not decrease the energy at all. You don't have any descent direction in the Hessian. On the other hand, in this case, it's very simple to solve the equations. The equations are really this times a vector g0 plus g of x equals 0, and so these are the equations where this is n by d matrix, and it's you want to find a solution with x equal 1. You do your kindergarten, random matrix theory, and you get that the threshold in this case is 1 over psi 0 plus 1. So there is a non-zero threshold, but alpha Hessian descent is 0. Okay, so we have a fix for this problem, but I will not go in detail in talking about it. I'll just say a few things about it. So basically, the idea is that you should take a few steps or a constant number of steps using the gradient. Here we have been discarding completely the gradient information. Instead, you should do a little bit doing the gradient. So the reality is that gradient descent would work, but okay, for the sake of proof, we analyze a different algorithm that we call the two phases algorithm. Okay, so let me just draw a picture. So the idea is that if you have this linear part, so this is an extreme case, but in general, every time that you have a linear part, the algorithm that I described is not optimal. And so what we do, what is the idea is that the set of solutions somehow, in this case, is mostly concentrated around a certain band that is not the center. So you have to move away from the center. And move in the first phase to the barycenter of where solution is. So first phase, move to barycenter of solutions. And the second phase, okay. Once you move to the barycenter of solution, you can restrict to, so let's call this x hat, and restrict to the subspace to SD minus 1 intersection x hat orthogonal. So you restrict to the band on the sphere orthogonal to this point. And this means basically adding one more equation, which is not okay, for what we are doing is not a big deal. And there will still be many solutions. And what happens is that if you do this, this will be now a new Gaussian process with a new psi. You can describe it with a nu psi that depends on x hat, and this nu psi will not have first derivative equals 0. So we apply Hessian descent. Okay. So you move to the barycenter, then you restrict to the orthogonal component, and on this orthogonal component we do Hessian descent. Now, how we do first phase? Okay, the way we do first phase is we use something that we have been developing over the years, that is approximate message passing. And I will not go in detail of how it works. And in the end, we get a theorem that says if alpha is less than a certain two-phase threshold that we can explicitly characterize, then we find solution. Not solution, but a near solution or rough solutions. Okay? And in particular, in this linear case, we get this threshold here that you can compute by elementary method. In the Hessian descent case, in the case in which psi prime at 0 is 0, you recover the Hessian descent threshold, but we have a more general formula. Okay? Now, a natural question is whether this two-phase threshold is the computational, fundamental computational threshold for this problem. As I said, there are gaps between this and the region in which we know there are solutions. So there is probably a hardness regime. Yeah.
Does the message passing tell you where x hat is? Or not?
Yeah. It's an iterative algorithm. It's basically it's very similar to gradient descent. You have an iteration of this type: xk plus 1, gradient of h at xk, and there is some extra term. Yeah, it's okay. Yeah, it's something very similar to that. Okay, the real way it works. Okay, I'll write it here. The real way it works, the iteration is xk plus 1 equal d f xk, and then zk transpose plus some residual terms, and then zk equal df xk plus some residual term. So it's some such iteration in which you keep computing Jacobian at the current point, add it up, and then you run a constant number of iterations of this, a large constant number of iterations, and that will be your X set. Okay, and I will not write the formula because it's not particularly. Okay, so any question about this? I want to spend last perhaps 5 minutes and then or 10 minutes about. Now, all of this was about finding a very rough notion of solution. So what I talked to so far was about finding points such that f of x is less than n times epsilon, right? Or small o of n, right? Now you might wonder, how good of a notion of solution is this? Is this a good notion of solution or not? In particular, this doesn't necessarily guarantee once you find such a point that close to it there is an actual solution, right? So the question is, what about actual solution? So now one has to give a solution, a definition, because you cannot give an explicit form of the solution. And okay, now so what we use is the definition that was given by Smale, Schubert-Smale, in the 90s, and they came up with this solution. We say that x0 is an approximate solution to f of x equals 0 if Newton method initialized at x0 satisfies xk minus z square less, or not square, doesn't matter, less or equal than 2 times e to the minus c k for some solution. Okay, so I say that the problem is solved if I can find one initialization after which I run Newton method and this converges doubly exponentially. Right? So this is there for some c constant. Okay, so the question is, can we find approximate solutions in the sense of Smale? And this is the last theorem.
Is the double exponential too strict, or is that natural to?
What? So this is the normal convergence of Newton method, right? Close to the minimum. So if you are close enough to the minimum, the local convergence of this. So the statement is that you can get close enough to the thing that the basic, right? Yeah, it's quadratic convergence, which I find a very confusing terminology. Okay, so the theorem, so this is the theorem that is not in the paper that is out. So this is, perhaps it's March 2024. It's a future theorem, hopefully. I mean, it's all written apart from. Okay, so in this case, we consider homogeneous in IAD case, not identically distributed case. In other words, what we have in the language before, we have the xi of q is q to the pi. the ith function is a polynomial that is homogeneous, but is of degree pi, and pi is completely arbitrary. This is actually the original setting of this problem. Okay? So for some p1, pn that are bigger than 2, because otherwise it's trivial, and arbitrary, possibly dependent on n and d. Okay, and the claim is that if the number of equation is less than d minus constant square root of d log d, so the ideal thing would be to do n equal d minus 1, but we need an extra square root of d factor. Then there is a polytime algorithm that finds approximate solution with high probability. Okay, and okay, what is the algorithm? Basically, the proof of this is based on the a more careful analysis of the same gradient descent algorithm, because we have to get to much more precise solution. And then in the last phase, we want to show that basically the function is nearly quadratic. So there is an actual solution close to it, and after that, you keep converging to it. So we need to, control, okay, so there is Hessian descent plus a phase of gradient descent, and then need finer control on the Hessian, and then control on the Jacobian near solution. The point is that the Jacobian, you cannot control it anywhere because there will be some saddle, there will be some degeneracy point, but near solution we can control it quite well. Okay, I think that's all.
Okay.